We're just going to give people a few minutes to trickle in here. I imagine we'll have a few more than you three. Not that you're ever not enough or anything like that. Just want to give as many people an opportunity to get started with the whole group. In the meantime, if you have specific questions that you would like me to cover, it would be a good time to go ahead and drop those in the chat if you have word problems or topics or anything like that. I'm also happy to hear your questions out loud as well.
Do you think you'd be able to go over like specifically some reaction yield and calorimetry?
Calorimetry. Yeah, we
Okay.
can totally do that. If you have specific questions, that would make my job a lot easier. Just because like making up some of these problems off the top of my head can be a little time consuming. But yeah, if you like find one or two of those, I'd be happy to try them out.
Yeah, I'll look for some.
Great,
Okay.
thank you. There will not be any calorimetry or enthalpy problems on this exam.
Cool. Then we don't have to worry about them.
Well,
Thank you.
you said reaction yields, right, Gia?
Yeah. Yeah.
I'd like to do
Reaction
one of
yields.
those.
Okay.
Just for people that come in after us. Well, that's probably enough time waiting for the stragglers. Why don't we go ahead and get started then? Um, Gia, did you find anything in particular you wanted me to do, or shall I make something up on the fly?
I can pull one up. I had opened the telemetry ones first.
Oh, okay.
This will load.
That's my bad. I probably should have thought about the
That's
question you were asking instead of just correcting your pronunciation. Sorry about that.
that's good.
Okay.
Okay. I can put one in the chat.
That'd be great. Thank you.
Okay. Thank you.
Excellent. All right. All right, according to your calculations, an experiment in the lab should have produced 25.90 grams of product. If you actually produce 17 grams, what is your percent yield? So something to remember about all of these percent yields and parts per million and billion and trillion and any of these ratios that we do in these chapters, it's always going to be the part, so the smaller portion, over the whole, which is the bigger portion. And so when it comes to reaction yields, assuming that you actually only have your product, then the smaller thing will always be what goes in the numerator, the bigger thing will always be what goes in the denominator. And then you just have to look at what units they're asking for, and here they're asking for percent. So percent means per 100, which means we'll multiply by 100 in the end. So for this particular equation, it becomes percent yield is equal to the part, which in this case is our actual yield. The actual yield is what you actually got, and it should be smaller than your theoretical yield, because things always work better in theory, but in practice you're going to have less stuff. And then of course times 100. So now that I've determined what my equation is going to be, I just have to go ahead and plug these values in. So we're given that it should have produced 25.9. That sounds a lot like theoretically it's 25.9. So I'm going to go ahead and drop that in for my theoretical. I'm including the units here just because it's always good practice to include them. However, percentages are by definition a unitless idea. We have actually produced 17.0 grams, and then we're going to multiply that by 100 in order to find our answer. So it'll be 17 divided by 25.9 times 100. And so we should get 65.63% yield. Ways that you can check your work on this problem. It should always be less than 100%. I'm not going to give you something where there's clearly been a mistake. In your lab classes, you might have gotten a value over 100%, but that's probably because you didn't dry your sample correctly, or there was unreacted starting material in it, or something like that. Typically speaking, we expect values less than 100%. You also have to have a positive value here. I can't imagine how you would get a negative one, but make sure it's a positive value less than 100%. Any questions on this one?
No, that's good.
Cool.
Thank you.
Yeah, of course. Open the floor up to any other questions you might have.
I got 65.637, so would you round up to 0.64?
So, oh, shoot, did I round incorrectly? Yes, I did round incorrectly, and you should round up, so that this should have been a 4. Other questions? About, like, literally anything.
Do you know fully what the structure of the test is going to be?
Yes, I do. What do you mean by structure?
Um, what would be, because I think there was the study guide that was in the announcement,
Uh-huh.
but some of it seemed like stuff that we may have not gone over yet. Will it all be included, or are there things that are like, these 5 things are definitely the best things to study? Let me see, I can't
There's
find
like way more than 5 things.
that. Yeah.
Okay. So in particular, Exam 2 study guide, I did edit this document this week, and I feel like it is correct. Each of these topics was covered in our textbook, any of those readings that I asked you guys to do. And any of these may be included on the exam, whether or not we had a homework assignment that was dedicated to that topic.
Okay.
And so things like dilution, we definitely did homework problems about dilution, right?
Yeah.
But things like strong versus weak acids, I can't remember if that was necessarily covered in the homework. However, it is helpful to know the difference between strong and weak acids, especially when you're trying to assign reaction classifications. Reaction classifications, by the way, definitely something that's going to be on this exam. And we talk about it right here. So if you knew what a strong acid was and you knew what a strong base was and you had both of those in the same reaction equation, you should say this is an acid-base neutralization reaction. That's the kind of information that I would be looking for there. Any other of these topics in particular that didn't seem familiar to you that you'd like me to go over?
Titrations. I wasn't super
Sure.
sure about.
We did get some homework problems about titration, didn't we?
I think a couple, but I think I just wasn't. I don't remember where they were.
That's okay. Let me see if I can find one. I suppose it'd actually probably just be quicker if I made one up. So let's see here. We're going to say that a 1.5 molar solution of HCl is titrated with a no, we'll say is used to titrate an unknown concentration solution of calcium hydroxide. If it takes 125 milliliters of acid to fully titrate 50 mLs of the CaOH2, what is the concentration of the CaOH2 solution? Okay, so this is a pretty typical type of titration question. Really, they're just word problems for dimensional analysis and stoichiometry. Don't get too hung up on the text. Try and just extract the numbers that are important, and then you're going to be converting from one substance into another. Now, in particular, I left off an essential piece of information when I wrote this problem. Could anybody tell me what it is?
The concentration.
Well, I didn't leave that off, right? That's the unknown that we're searching for. There's another piece of information we need to be able to convert in between two different substances.
The chemical equation?
The chemical equation, very good. Sorry, my dog is playing with the door. We have HCl plus some amount of CaOH2 will react to yield what? What is the product of any acid-base neutralization reaction? You're always going to get a water molecule and some salt. Salt in these contexts just means some kind of a neutral ionic compound. And so we have H2O plus CaCl2. I know it's CaCl2 because calcium is one of our main group elements, and so it always makes the charge that you would expect, which is 2+. It's two spaces in from the beginning of the row, so Ca2+ means we need to balance it with two chlorides. Now that I know what my individual pieces are, I can balance this equation. I'm noticing right off the bat that I've got H+ coming from this guy, and I've got 2 OH minuses coming from that one. So I'll need 2 of these H pluses to react with the 2 OH minuses. Generally speaking, acid-base neutralization occurs like this, where you have an H plus, an OH minus, and they will react to yield an H2O. So it's just a trick for balancing these equations. The 2 H's react with the 2 OH's, and that'll make 2 H2O's. Now I'm going to go ahead and just make sure that all my other stuff is balanced. I expect to have 1 calcium, which I do on the product side, and I expect to have 2 chlorides, which I also see on my product side. So this is now a balanced chemical equation. From here, it's pretty much just dimensional analysis. We're going to take one of our starting materials and we'll convert it into moles, then we'll convert it into the other substance, and then finally that should be able to give us the desired concentration of our solution. So I see that we have 1.5 molar solution of HCl, and I see that it took 125 milliliters to fully titrate. So I think that's a good starting point. I'll write down 125 mLs of HCl. Make sure you're including the number, the unit, and the chemical identity with every one of your steps in the dimensional analysis. The reason we do that is because we're going to have to convert our chemical identities from one substance into another somewhere around the middle of these problems. Without those chemical identities, it becomes really easy to get lost, not remember which concentration stayed with what compound, etc. So before I start worrying about the chemical identities, it's important for us to have this in the correct units. So I see that we have milliliters here, but 1.5 molar. Remember that molar, capital M, is moles over liters. I strongly recommend anytime you see that capital M, write it down as moles over liters right away. And so 1.5 molar is actually 1.5 moles per liter. If I wanted to use this term, I would have to have my HCl in terms of liters, not milliliters. So I'm going to begin by transferring those units. To do that, we have 1 liter on the top, 1,000 milliliters on the bottom. That'll make milliliters cancel with milliliters. Now I have liters of my HCl solution left. So I can multiply this by my molarity for the HCl. 1.5 moles of HCl are contained within every 1 liter of this HCl solution. So my liters of HCl cancels with my liters of HCl, and now I know how many moles of HCl are contained in this sample. From there, this is when we have to convert in between the two substances. Moles is the link. It tells us we have this quantity of these pieces, and then we convert it into quantities of other stuff. In this case, we're going from HCl into the calcium hydroxide. So the mole ratio, based on our balanced chemical equation, we'll get 1 CaOH2 mole for every 2 HCl moles. So moles of HCl cancel with moles of HCl. I now know how many moles of calcium hydroxide there are. The final step here, since we want the concentration, we're going to get that concentration in terms of molarity, since I was given molarity in this problem. To do that, we need to multiply this, or rather I should say divide it by the volume of our calcium hydroxide solution. So some people might choose to, give me a second, guys. I've just received a message that says imminent threat alert. There's a tornado apparently coming to Baltimore. I'm going to end the call, and if my house is still here, I will hop back on in like 10 or 15 minutes. All right? Bye.